Hi, here we are discussing about a project design and implementations of unified digital clock and stopwatch systems using a finite state machines and multiplexed 7-segment display. Here, the digital clocks and stopwatches are widely used in daily applications such as consumer electronics, embedded devices, portable medical instrument, and time monitoring systems, or they provide a simple and accurate time tracking functions. These systems offers advantages like low cost, user-friendly operations, and highly reliability. However, they often face disadvantages such as hardware redundancy and high power consumptions and limited integrations when clock and stopwatches functions are implemented separately. The main problem addressed this works is a lack of unified architectures that can perform both digital clock and stopwatch operations using shared resources, which leads to inefficient hardware utilizations and increased complexity in existing design. This conventional systems generally use independent controls and dedicated display drivers, resulting in additional overhead. To overcome these limitations, we propose a finite state machine based architecture that integrate both digital clock and stopwatches module into a single design with a common display hardware. This systems employs multiplexers and control signals to switch seamlessly between a clock and stopwatches modes, while state such as ideal, hour, minute, second, and pause are clearly managed through FSM logic. The novelty of this work lies in the resource sharing approaches, where a common 7-segment display is driven by multiplexed output, thereby reducing area and power and switching complexity without compromising accuracy. The proposed design is implemented and tested using a hardware descriptions language code using Verla HDLs and simulated on FPGA based platforms, ensuring precious timing, functional correctness, and display reliability. Okay, now we can verify the paper. So here we have taken a number of reference paper for this work. Okay, so this is one of the paper, design and implementations of digital clock with the stopwatches on FPGA. Okay, and this is a digital clock using FPGA, and this is the implementations of digital clock with the stopwatches on FPGA, and this one is a design and implementations of digital clock using 7-segment display. Okay, so here this work they will be integrated the digital clock and the stopwatches in a single architectures. Okay, so which means they used for one digital clock model, that is a counter model, and stopwatch models between multiplexers. Okay, so using switching between these multiplexers, okay, so they will be displayed the digital clock and the stopwatches. Okay, but here what we implemented means that this work we integrated with the novelty architectures in a state machine way. Okay, and we reduce the logic sizes and power consumptions. Okay, so this is our state machine logic. Okay, so this is a digital clock state machines. Okay, so here we start from the ideal state and seconds parallelly executing the count. Okay, and once the condition reached the seconds maximum value, so then it will move for the minutes and also for hours, and it will be incrementing. Okay, so this is a stopwatch. It's additional mode, it's having a stop signals and also for pause mode. Okay, so as per that it will be working for 24 hours. Okay, and this is a top model architecture. Okay, so here we have used two multiplexers. Why? Because one multiplexers it will be switching for digital clock and the stopwatches. Okay, so another multiplexers it will be required for the 7-segment display. So which one we need to take? Actually in the 7-segment we have 4 display in hardware, so that's why the 4 bit register A, register B, register C, and D we are taken as a output. Okay, so here register A means it will be come with a one nibble off, that means 3 down to 0. Okay, so as per that we splitted the value with the LSB and MSB. Okay, so then after we need to give any two values here. So second means seconds LSB and minutes LSB MSB, and hour means hour LSB and MSB. Okay, so that's why we switching here. For 0 means the seconds and minutes it will be shown in the hardware. Okay, and if it is 1 means a hour it will be shown in the hardware. So however, in the time of hour, the register A and register B will be active, and register C and register D it will be goes to 0. Okay, so this is a mode we have handled here. Okay, and we have implemented all the coding separately. Okay, so here this is a digital clock coding. Okay, and this one is a stopwatch coding separately, and this is a digital clock with a stopwatch integration, and this one is a digital clock with a stopwatch and a 7-segment display integration. Okay, and this all coding we have simulated in modelism. Okay, so this is a digital clock simulation. Okay, so here you can verify the seconds, okay, and minutes and hour. Okay, so here hour it will be executing for 12 hours. Okay, so after 12 it goes to 1. Okay, and this is the stopwatch integrations. So what is the conditions is a priority means while the pass input it will be pass the value. Okay, after the pass it will be released, it will start from the previous state, it's the previous values it will be start. Okay, so and this one is a digital clock and the stopwatch integrations with the multiplexers. Okay, and this one is a hardware implementations for 7-segment digit 1 to reset output. Okay, and this all things we have synthesized in Xilinx FPGA. Okay, so here this is a features, slicer resistors, LUT, occupied slicers, IOB. Okay, and the synthesis report. Okay, so 3.295 nanoseconds. Okay, the same processor it will be handled for all the thing. Okay, so this is a stopwatch and this is a digital clock and stopwatch integration, and this is a 7-segment integration. Finally, the 7-segment integrations we integrated this work in a hardware. Okay, so here this is a summary. Okay, so here you can verify that sliced registers, LUT, and occupied slicers, IOB. Okay, and the synthesis report it will be showing the delay for hardware integration 4.986 nanoseconds. Okay, and this is a RTL schematic for this project. Okay, so here we have used clock divider and digital clock, stopwatch, 2 multiplexers and 1 7-segment. Okay, so this output we can easily seen in the hardware model. Yeah, this is a hardware output. Okay, so here you can verify that. So once we start from reset, okay, so this digital clock it will be start from 1. Okay, so here the first bit is a start bit, and second bit is a pass bit, and third bit is a select for digital clock and stopwatches, and fourth bit is using for the MSB. Okay, so now it will be working on digital clock. Okay, so seconds it will be counting 31, 32, 33, 34, 35. Once it will be reached the 59, it will automatically move to minutes count 1. Okay, so you can verify it. So for now 50, right? So 52, 53, 54, 55, 56. Yeah, okay, now minutes goes to 1. Okay, so now we can check the MSB part. So the MSB of the output is it will be maintaining 1. Okay, 0001, that is a hour value. Okay, so at the same time we can check the stopwatches. So here the stopwatches it will be counting the same value, but we can pass the value here. Now I will be pass the value, it's equal to 0127. Okay, so once it will be ready, then only it will be counting. Okay, so this is a concept of this architecture. Okay, and here we have compared this all the features of synthesized report in the comparisons table: digital clock, stopwatch, and digital clock and stopwatch integrations with multiplexers, and hardware implementations with the 7-segment. Okay, and we have written abstract document for this project. Okay, so here you can verify that title, base paper abstract, proposed abstract, and objective, existing system, disadvantages, and proposed systems with the state machines, and detailed architecture of the proposed concept, advantages, and the related notes. Okay, and finally we come up with the literature review. Okay, and references. Okay, thank you.